Hi, this is my video number 17. Okay, I'll talk on the tangential and normal component of the acceleration. Yeah. Tangential and normal component of the acceleration. Alright, so let me begin with a theorem. We know that in the previous video I've given you the definition of the vector unit normal and vector unit tangent, and also we have the definition that the acceleration is actually double differentiation of the position vector. Yeah, so that's what we know. Now let's begin with the theorem. So theorem says that the acceleration A can be written as we have t plus an n, yeah, where at is v prime and an is kappa v squared, and v is the magnitude of vector v, which is ds dt, and t and n are vector unit, tangent and normal respectively. Vector unit, tangent and normal respectively. Okay, so what does this theorem says that if we have a curve with position vector, let's say rt, and we know that v, the velocity is given as r prime t, and a is given as, we differentiate v or differentiate r twice with respect to t, so that gives us the acceleration. So this form of representation we write in terms of unit vector I, j and k. Alright, but now instead of writing in terms of I, j, k, we can write the acceleration of a vector or of a particle as the unit tangent and as well as unit normal, where of course we have some factor down in front, where this at is given as v prime here and an is given as kappa v squared, where this kappa is the curvature. Okay, so let's prove this. Right, so let's prove this theorem. So let v magnitude of v, this is given here, right? Then the speed of the particle, sorry, not then. So let v, so this v as a, we denote that as a speed of the particle, and t, the unit normal, which is r prime over magnitude of r prime. Alright, this is equal to the r prime is v prime, r time is v over this magnitude of v, and magnitude of vector v is given as v. This is from what we given here. So this is equal to, we have v t over v. So note that, so this is also, so v of t v t. Okay, so note that the numerator here is a vector, whereas the denominator here, this is a scalar. So v without bar here, this is a scalar. So there are two different things here. Okay, so from here you can write this v as a v, that v times t. So therefore we have v of t, this is vt, without that, t. Okay, we just multiply the denominator to the right, so to the left. So this is what we have. Okay, so if we differentiate this with respect to t, differentiate both sides, with respect to t, so what we have, that give you v prime, which is our a. Okay, and the right hand side, what we have is that v prime t tt plus vt t prime t. Okay, so but we have kappa is given as, or we define kappa as t prime t over r prime t, and r prime t is a v vector v, which is the scalar v. So what we have here is, this is t prime t over v of t. Okay, so from here, so we have the magnitude of t prime can be written as the magnitude of t prime t, that can be written as, we have v t kappa. Alright, so what we want to show, actually we want to show this, that ATAN is actually given by that and that. So this is what we want to show. Now, so we have those t, and then also we have normal, vector unit normal is t prime over magnitude of t prime. Okay, so from here we can write t prime of t, this is t prime magnitude of t prime of t times n. That. So therefore we have from this relation here. Okay, let's denote this as a star, say. Okay, so therefore from star, we have found what we have found. We have found v prime, where v prime is written here. That's v prime. We just need to substitute the v prime. This is your at. Compare with that. We compare with what? So we have att ant. So we have AT. In this case, our AT is given as where is it? Here. This is our AT, which is V prime, and next is our AN. So this is our AN. Alright, and this AN, VT is given here. So VT, where is VT? VT is given here. That's VT. You just VT T prime. So T prime, we have this. This is T prime. Okay, T prime, we just substitute there. So we have V and we have K. And then we use this denotation as well, because for the T prime, then you can just substitute everything. So therefore we have A is given as V prime T plus, we have where is it, T prime, okay, so V T prime is here. Okay, this is magnitude T prime, so N is we need to substitute here. So what we have, this is kappa V squared T N. Okay, this is what we want to prove. Okay, I think we can get that already. So now this is our A. We just substitute this T prime with this, and just substitute this T here. So you have V1 here, the another one, so V squared, and we have kappa. So V squared kappa T. So okay. Okay. So this is the representation of acceleration in plane, in plane, xy plane, in terms of tangential and normal vector, unit tangent vector, unit tangent, and unit vector, unit vector. Okay. Now, if you look at the, let's say we have that curve, yeah, with position vector RT, of course. Then for at point T, say this is our RT. Okay, so we have a tangent, and we can have the vector unit tangent here. The vector unit tangent, this is, and along that multiply by that some factor AT. And also we have N, our N pointed the direction of curve is turning, so means, so in that case this is our N. Okay, the unit vector N, this is N unit vector here, this is unit vector there, T, then the magnitude AT. Here we have AN, so therefore our A is given, the summation of those two, so we have somewhere here. So this is our A. Okay. Now let me write this in word. So T gives the direction of the motion, and N points in the direction the curve is turning. Alright, so in this case we don't have B. What does it mean? We don't have B here. We don't have B, nor B, which means so we have only T and A. So it means there's just 2 dimension. We don't have 3 dimension. So because if you have B pointed towards you, so means that A always lies in the plane of T and N, which is the osculating plane. Osculating plane. Okay. Now I'm going to show you that we know that the acceleration A can be written as AT T plus ANN, right? So I've given this in the theorem just now, where our AT is actually magnitude of V prime, which is V prime, okay, and AN is given as kappa V squared. Is that correct? Yes. Now we want to show that the AT can also be written as R prime dot R double prime divided by R prime, that, and AN can be written as R prime cross R double prime over magnitude of R prime. So we're going to prove this, that AT, where AT previously said that can be written as ATTANN, where AT is given as that and AN given as that. Now we're going to prove that other form of AT and AN can be written as the dot product between R and R prime and R double prime, and AN is R prime cross product with R double prime divided the magnitude of R prime. So let's prove this thing. So if we take the dot product, proof. Take the dot product of VT with A. So what we have? So we multiply this on the left side. So we have V dot A. On the right side we have, this is equal to VT dot A, and our A is given as here as this. So our A is, we have VT dot, okay, so we have V prime, this is V prime T, V prime T plus kappa V squared N. So you can have here, this is v prime t dot t plus, so we have kappa v cube t dot n, and we know that this is a better unit t dot t, so this is 1. Alright, tn that give you 0 because they are perpendicular. So what left is we have this is equal to v prime. Okay, so from here what we have, v prime is actually v dot a over v, and this is v is r prime, yeah, v is r prime, dot a is r double prime, and v is magnitude of r prime, and this is our so v prime is at, yeah, v prime is at, so this is equal to at. So therefore we have proved that at can be written as that. And for the other one, an, from the given an here, an is kappa v squared, yeah, and we have an which is kappa n v squared. This is equal to, so kappa we have shown in the previous video, in the previous lecture, that it can be written as r prime cross r double prime over r prime cube. You can just check the appropriate notes. Alright, and then and our v is given as r prime squared because we have v squared here. So therefore simplify this, that give you r prime times r double prime over r prime. That's it. Okay, so what we did here is that, okay, that first I have shown you that the acceleration can also be written in terms of tangential and normal component, where AT/AN is given as this. This is your AT, this is your AN, yeah, or you can also just write it straight away like this. Okay, so this part here we have proved that from the position vector r, yeah, from the position vector r, we can write that at as that, and then I have described to you what is a, or acceleration, in terms of position vector, and as well I have shown you that the at can be written in terms of r prime and r double prime, as well as an can be written as that. So that's the proof. Okay, now let's see example. I have an example here to find an and at. Let's say example, we have RT, let's say, given as t squared, and t cubed. Okay, find the tangential and normal component, tangential and normal components of acceleration. acceleration. Okay. Given R, you want to find the tangential and normal component of the acceleration. So I think the easiest way to use, of course, what we want to find is AT, where AT is given as R prime dot R double prime, magnitude of R prime, and we also want to find AN, which is given as magnitude of R prime times R double prime over magnitude of R prime. So using this is much easier rather than you have to find the curvature and so on and so forth. Okay, so to find those things we're given that. So what we need to find is just let's say solution. We need to find R prime. Now R prime is given as those 2t and 3t squared, and also we need R double prime. This is 2 to 6t, and what else we need? The magnitude of R prime. So you can find magnitude of R prime. This is square root of 4t squared plus 4t squared plus 9t4, right? So you can write this is 8t squared, so t squared you can take out. So what left is you have t square root 8 plus 9t squared, right? Okay, so therefore you can find AT. So therefore AT is given as, we have R prime here 2t 6t squared dot R double prime is 2 6t, and magnitude of R prime given by that. So we have t 8 plus 9t squared. So what we have here, this is, so we have, this is 40, this is 40, so that 40 8t. Here you have 18 60. Alright, so we have 8 plus 8 plus what is it? 18 t cubed, right? So you have t squared here, and you have t here, so 18 t cubed. Divide by those, t 8 plus 9t squared. Okay, so this is 8t. Okay, so t you can cancel out those t, so now becomes squared. So we have here 8 plus 18t squared over square root 8 plus 9t squared. And for an, we can find an. An is the magnitude of R prime times R double prime over magnitude of R prime. This will give you, we have 2t 3t squared times 2 to 6t over t 8 plus 9t squared. So this is magnitude. And if you do this, what we have, you're going to have magnitude of 60 squared, negative 60 squared, and 0. Magnitude of those. So divide over t over 8 plus 90 squared. So this will give you just find the magnitude of those. So we have 36 T4, we have 2, so 72 T4, yeah. So we have square root 72 T4 over T8 plus 9T squared. Of course, here T4 you can take out, 72 you can find the appropriate factor. So then you have, this is given as 6 square root 2T over 8 plus 9T squared. Okay, so you have this one, and we have 80 is given here. So that's what the question one. We want to find the component of tangent, so which is 80, that, and we want to find the component of normal, which is an. Then we found this thing. Okay, so with that example, and I have shown you how to find those an and 80. I think I stop here. But for your exercise, it might be good if you can find, as an exercise, find those an, and 80, find 80 and an using, find those things using 80 is equal to v prime and an equal to kappa v squared, where your v is actually magnitude of v, which is, this is ds over dt. Okay, try this as an exercise. So with that, I think I'll stop here. Before, for the next lecture, I will go on the function of several variable. All right, so for this part we finish. Thank you. Bye.